So let me show you. Let me give you an example of where this gets to be important. Um, I have a block on an incline. There's no friction. What direction do you think the acceleration is going to be in? So the acceleration is going to be in this direction. So I'm going to guess acceleration in that direction. So I'm going to call everything going down positive, okay? Same problem, right? What direction am I going to call positive here? To the right. Okay. So you're gonna suggest that that's the direction for acceleration, right? So if we know intuitively a block on an incline, right? A kid in a snowsuit on Hull after freezing rain, right? This is, this might as well be, might as well be Lexi at the top of Hull with her, nylon wind pants, right? Sitting down and saying, and you're yelling, go for it, right? As she slides down the hill, I'll block traffic, She would, but you just said the acceleration's in that direction.
What?
You just told me to you pointed up the incline for the acceleration.
The acceleration's like also going down.
Right. So the point is only that's why it's important to decide what direction you're going to declare the acceleration in.
It's not like that determines whether or not she's going down or
No,
up.
it just tells you whether or not, when I draw my free diagram, what direction plus and minus are in.
I thought we were sort of universally assuming that counting it down one direction, it's negative, or if it's upward, right?
Right, but I agree. But I built my free body diagram, right? And then I told you what direction, then I told you what the value for tension was, right? So before I knew the tension, I made a guess about the direction for acceleration, right? So that's why we do it. We do that just so we decide we define our coordinate system. Okay, that's all that. Okay. Okay. I have two boxes on a frictionless surface touching each other. I have an applied force of 3 newtons in this direction. And I want to know what the acceleration of the system is. Isabel, what's the first step? Create a free body diagram. So what does the free body, so everybody do that, right? Draw a free body diagram for me. Remember, free body diagrams look at one object. So how many free body diagrams do I need to have for this? Isabella says 2. So please draw me 2 free body diagrams. 2 kg, 4 kg. So what do we have? Nick, what do you have for forces on the 2-kilogram block? So I've got 3 newtons in this direction. Wonderful. F applied. It's actually normal force, but I'll use F applied for the time. That's great. What else? Gravity going down. 20 newtons, right? Normal force going up. I kind of ran out of space, but that's okay. And then I have this block here pushing back. So I have the force of the second block on the first block. And I've been a little, well, sometimes you draw the forces, it's okay to draw the forces going into the object. What forces do I have on the second block? Yep. So you have F of 1 on 2. What else do you have?
You have again gravity.
Right. You have gravity, bigger gravity, and a bigger normal force. Okay. If there's no friction, we can basically not have to worry about the forces in the vertical direction. So we will do sum of the forces in the x direction on number 1 is, I have a F21 minus a 3 Newton, and that's going to equal mass of 1 times the acceleration of 1. And for this forces, some of the forces in the x direction on the second one are strictly going to be force of 1 on 2, which is equal to m2a. F of 1 on 2, magnitude of f of 1 on 2 is equal to the magnitude of f of 2 on 1. So I can play my game where I add them together and I get, oh, you know what? I made a mistake here. So some of the forces on the first block are going to be the applied force of 3 newtons minus the force that the block is being pushed back by. Some of the forces in the x direction on the second block, on this block, are F12, which is going to equal M2A. I can basically add these two together, and I get 3 newtons is equal to M1 plus M2 times A. So without a lot of effort, I get an acceleration of half a meter per second squared. And just because I'm interested in the force between the two blocks is just M2A, force of 1 on 2 is going to be 4 times a half 2 newtons. What happens that...
So the first box has the force, but also has the other box pushing.
I'm going to do that right now. So what's worth looking at is, remember that the sum of the forces in the x direction on the first block looked like a 3 Newton minus an F of 2 on 1 is equal to M1 times A. So F of 2 on 1 is going to be 3 newtons minus M1A. 3 newtons minus M1 was 2 times 1, sorry, times a half, is equal to that same 2 newtons, right? Or if you look at it from the other perspective and solve for the acceleration, you can say M1A is 3 newtons minus F of 2 on 1, 3 newtons minus the 2 newtons that I found from the first part, from the first equation, would give me M1A is 1 newton, so A is equal to a half meter per second squared. So the results are consistent, right?
For the box on the left and the free body diagram, you have the force this way and the opposite way. For the box on the right, you only have the force to the right. So you the box on the right accelerates faster.
No, because these,
Oh, it's smaller.
this box is bigger, but think about it. The only force acting on this block here is the force from this block. Okay, So, a couple just closing notes. One, circular motion lab due tomorrow. Centripetal floor. I'm going to ask you to finish up the apparent weightlessness. On Schoology, there is an assignment to have you do a handful of problems from this packet. I'd like you to certainly give it a try so we have something to talk about tomorrow in class.